Okay, so this is the extra credit for test version A, and we start off with this scenario. Approximately 5% of all hobbits born in the Shire are from multiple births, that's twins, triplets, etc. Of the hobbits born in the Shire who are from multiple births, 65% have hairy feet. Of the hobbits born in the Shire who are from single births, 10% do not have hairy feet. So right away, I see that I have three numbers. I don't know. It just tends to be that if I have a story and there's three numbers, this tends to be one that I'm going to solve using a table. And when I look at it further, I see that I have two variables. I have multiple births, and I also have, in addition, I also have the hairy feet. So those are my two variables, whether they have hairy feet or not, or whether from single or multiple births. And the next thing that comes to mind that I look at, I see the word of. That means from the group, which means we typically are talking about some sort of conditional. All of those are great hints that I'm working with a table. So I'm going to take time right now, and we're going to go ahead and build that table based on based on this question. Now, what I see in this scenario is I need to first off identify the numbers associated with only a single variable. Approximately 5% of all hobbits born in the Shire are from multiple births. This right here looks like it's a single variable. It looks like it's only tied with multiple births. It does not look like it's tied to hairy feet. Of the hobbits born in the Shire who are from multiple births, 65% have hairy feet. The of tells me that I'm working with a conditional, and I have multiple births and hairy feet. So this one is tied to two variables. And then of, again, we have the conditional, and who are from single births, 10% do not have hairy feet. So we have the single births and hairy feet tied together, or not hairy feet. So this is also two variables. And the word of kind of tell me that it was from the group. So it's probably going to be a two variable because it was a condition. So I'm going to go ahead and start my table off, and I'll just start off by drawing my window. And I'm not going to do this very rapidly, so you're going to just have to hang on as I go through it. Okay, so first number, the most difficult, 1.0. I like getting that one down immediately because it's like, hey, you know what? I know something when I put that one down. And so I'm not starting with a completely blank table. So right here, I always put the first, the one that's a single variable, I always place it here. So this is going to be 0.05. So I can go ahead and copy that over because 1 minus 0.05 is 0.95. And then I'm going to write that relatively small. So this is going to be 0.05. And this is going to be 0.05. And this is going to be 0.95. And this is 0.95. At this point, I'm going to go ahead and label my table out. 5% are born in the Shire are from multiple births. So this is multiple births, MB for multiple births. And I'm kind of efficient, so not multiple births. I'll put an S for single. All right. And over here we have hairy feet, and then not hairy feet, because that's what we're working with. So, of the hobbits born in the Shire who are from multiple births, so I'm looking at this column, 65% have hairy feet. So this tells me right here, multiple births, hairy feet, they intersect right there. This is this group. 1 minus 0.65 is 0.35. And I'm going to go ahead and multiply those out real quickly. So we have 0.05 times 0.65. And that gives me 0.0325. All right. And then 0.05 times 0.35. I end up getting 0.0175. Now, as a check, I'm just going to add those two numbers up to make sure that they add up to the 0.05. They do. So there's a very high likelihood that that I've done this part correct because I've checked this out. The next one. Of the hobbits born in the Shire who are from multiple births, 65% have hairy feet. We've done that. Of the hobbits born in the Shire who are from single births, so in other words, we're looking at this column, 10% do not have hairy feet. So not hairy feet and single bursts, or not a multiple burst. So this is going to be 0.10 that tells us where this goes. And this is going to be 0.90. So we're going to go ahead and multiply those out. So when I do that, 0.95 times the 0.9, I end up getting 0.855. And then I have 0.95 times 0.9. And this is, oops, the 0.95 times the 0.1. That gives me 0.095. And once again, as a check, I'm just going to add these two together, make sure that they add up to 0.95. They do. So there's a good likelihood that I've done this part correctly. Now we're going to go ahead and add horizontally. So 0.0325 plus 0.855, and that gives me 0.8875. And we have 0.0175 plus the 0.095 is 0.1125. And then if I add these two values vertically, I have a check, and they sum up to one whole. So there's a good likelihood, it's not guaranteed, but there's a very good likelihood that we've checked out our table, set it up, and it looks like we probably have it correct, because everything we add up horizontally and we add up vertically. So we should now be able to start answering some questions. So the first question is, what is the probability that a hobbit born in the Shire is from multiple births and does not have hairy feet? Okay, we have a key word here. This says and. And tells me I'm working with the intersection. So I'm looking for the intersection of multiple births and not hairy feet. So multiple births is here, not hairy feet is there. So the answer to number one is simply this, reading this number straight off the table, 0.0175. Moving on to number two. What is the population of hobbits born in the Shire who do not, what percent of the population born in the Shire do not have hairy feet? Well, have hairy feet, this is right here, not have hairy feet. And it's like, oh, I just read all the way across, and this is 0.1125. Going on to number three. What proportion of hobbits born in the Shire have hairy feet or are from multiple births? This is a key phrase. This right here tells me I'm looking for the union. All right, so this tells me I'm looking for the union. So there's two ways to do this, and I'm going to actually go through both of them. So multiple births have hairy feet or for multiple births. So we're looking for the probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. All right, so we have hairy feet or multiple births. And so this is going to be hairy feet, this is going to be multiple births, and this is the intersection of hairy feet and multiple births. Well, the probability of hairy feet is 0.8875. And I'm reading that off of this part of the table. The probability of multiple births is 0.05. And the intersection is 0.0325. So if I take the calculator, I should be able to go 0.8875 plus 0.05 minus 0.0325, and I end up getting 0.905. And that's the way I think is more logical to think about the answer, because we're using the general addition rule, and as such, I think this is a good way to go. Now, there is a shortcut to it. but I don't expect you to necessarily recognize it. And that is, I could have, get a yellow highlighter, I could have just looked at 0.0175, 0.0325, and 0.855. And if I add up those values, I'm going to get exactly the same thing. All right? So 0.0175 plus 0.0325 plus 0.855, and that's 0.905. And this would be like if we had a done this with a Venn diagram, this would be like, okay, we have the part, it would look something like this. This part would be 0.0175. This part would have been 0.855. And this would part right here, the overlap would have been 0.0325. So if we'd done a Venn diagram, it would have looked something like that. And that's why that works. Although for me, I like using the general addition rule because we do it over and over again and we use it all the time. So A plus B minus the intersection is the way I would have gone about it. And essentially that was this value, these two values summed, and then I needed to circle out the overlap because it was counted twice. It was counted once with multiple bursts and it was counted once with hairy feet. All right, moving on. Number 4, what is the probability that a hobbit born in the Char is not from multiple bursts and does not have hairy feet? So here again, once again, we're using the word and. And the word and is an intersection word. So I know I'm looking for not from multiple bursts. Well, not multiple bursts is this column. And I'll just go ahead and circle this. So it's not this column. I mean, we're looking at this column because it's a not multiple burst. And does not have hairy feet. And not hairy feet is right here. So that's my intersection. So number 4 is 0.095 because there's my intersection right there, and that's my answer from that table. All right, moving on. It says number 5 is, given the probabilities D equals 0.3, D union M equals 0.7, what's the probability of M if D and M are mutually exclusive? So as a reminder, mutually exclusive means there's no overlap. So whenever I see this, I always think of the general addition rule. And the general addition rule is going to be for this probability of D union M equals the probability of D plus the probability of M minus the probability of D and M. But this, we know a couple things. First off, they tell us this is 0.7. They tell us D is 0.3. We don't know M, we're looking for M. Minus, we need the intersection, but there is no intersection because there's no overlap because they're mutually exclusive or disjoint. So this is 0, so I don't have to worry about this. So when I do my math, 0.7 minus 0.3 is just 0.4, so 0.4 equals M, and that's my answer. 0.4 equal to M. Okay, so that one takes us for number 5. Moving on to number 6. Given the probabilities D equals 0.2 and DUM equals 0.8, what's the probability of M if D and M are independent? Once again, they gave me this, I have this symbol. This tells me I'm working with the general addition rule. So probability of D UM equals the probability of D plus the probability of M minus the probability of D intersect M. Okay? All right. So let's plug in what we know. We know that DUM is 0.8. And we know this is 0.2. We don't know M. And we're a little bit stuck here, all right? Because we need to find the intersection and we don't have it. but they've told us something. They've told us that this right here is independent. Now, if they're independent, we know that the probability of D and M equals the probability of D times the probability of M. So in this case, this is 0.2 M. All right, that's all we know. We just know that's 0.2 M. Well, I'm not sure what to do, but I'm going to go ahead and plug that in. And it turns out I now only have one variable that I don't know. So I'm going to subtract this from here, and I get 0.6 equals M minus 0.2 M. So this is 1 M minus 0.2 M equals 0.8 M. Divide both sides by 0.8. And I get M equals 0.75. So that right there is my answer to number 6. M is 0.75. Okay? And please note that all I did is because this right here equals this, I substituted that in right there. Okay, moving on. Each of the faces of a fair-sided 6-number cube is numbered with the numbers 1 through 6, with a different number appearing on each face. 2 such number cubes will be tossed, and the sum of the numbers appearing on the faces that land up will be recorded. What's the probability that the sum will be 4, given that the sum is less than 7? Okay, so every time I have a situation where I have 2 of something, I'm making a table or a sample space. In this case, it's the dice problems, which are generally pretty famous, and they show up a lot. And here they showed up on this test. So I need to make a table, a sample space for this. And here I go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2. And by the way, this takes a little bit of time. It does. But if you timed me out, I'm probably doing this in under a minute, I think. If not, I'm sure it's under 90 seconds, which means I can do this problem in less than 2 minutes. And anytime that we can do a problem in 2 minutes, we are fine with our timeline. So the other thing is, yes, this problem takes a little bit of time, and I mean, there's no doubt that it does. But this is one that I should always get right. If I take the time to make this table up. And I don't mind spending 2 minutes on a problem that I know I'm going to get right. So here we go. Taking a little bit of trouble to do this. All right, and you could have abbreviated the table, and I'm not going to go over that, but if you say, hey, I saw a shortcut where I didn't need to draw the whole table, I could draw part of it, that's great. So in this particular case, it says, given what's the probability the sum will equal 4. So we're looking for this, given that the sum is less than or equal to 7. So let's deal with the given first. And please remember, anytime you have a given was always in the denominator, and the intersection is always on top. So given, and then we have the intersection on top. So it says given that it's less than or equal to 7. That means I'm looking to all of these values right there. Now, some of you are really smart and you can count all of that stuff. I mean, and you know what that number is real quickly. I'm not. I'm going to count this up, and I'll probably going to count it twice because counting is not my strength. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So I ended up getting 21 as my given, because these numbers, 1 plus 6, 2 plus 5, 3, 4, all these sum to 7, and I need to be less. So these are the area. Those are the ones that I'm interested in. Now, they said that the sum will be 4. Well, it said equals 4, not less than 4, or greater than 4. So these values right here are the ones that equal 4. So I ended up with 3 over 21. And when I divide that out, 3 divided by 21, oops, turn the calculator back on, 3 divided by 21, I end up getting 0.1429 or 0.1428 if you truncate it. So I'm just going to write 0.1428. Okay? And regardless whether you rounded up to 0.1429 or you had 0.1428, we counted that correct. Okay? So here we go, moving on. An administrator at Reagan estimates, and so that was number 7, so we are now on to number 8. Administrator at Reagan estimates that 20% of the cars, I should slide this down, in the parking lot do not have valid parking stickers. What's the probability that a random check of 8 vehicles in the parking lot that at least one does not have a valid parking sticker? Well, now that we talked on binomial, you can look at this as a different perspective, but I'm going to do this with a non-binomial method. All right, with a non-binomial method, we're going to sit there and go, well, what's the probability of random checks of vehicles in the parking lot that at least one, and we know when we do at least, it's 1 minus, and we want, and by the way, we had 8 vehicles, so 0, 1, 2, 3, 4, 5, 6, 7, 8. At least one means it could be any one of those. But we can subtract out the probability of 0, 1 minus the probability of 0. Okay, so let's take a look at that. So when we're dealing with an at least problem, we're dealing with the complement. So in this case, we're looking at 1 minus 0.8 to the, oh, excuse me, yeah, 1 minus 0.8, because this was 1 minus 0.2 gives me this value, raised to the 8th power. All right, so that's what we knew before. So 1 minus 0.8 caret 8. And I end up getting 0.8322. Now you're going, okay, but we now know something about the binomial. All right, and maybe it'd be easier for you to think of it this way. It's still an at least problem. So 1 minus, and we have a fixed number of trials. So we have a fixed number of trials, and our number of trials in this case is 8. Our probability of success is 0.2. Probability of failure, Q, is 1 minus 0.2 or 0.8. All right, so if I were looking at this, I would sit there and go, you know what? I have multiple values, and so it's going to be 1 minus the binom, multiple values, CDF, trials is 8, probability 0.2, and my X value, the one that I'm subtracting, would be the 0. So that would be what we plug into the calculator, and I am going to show you this, and if I'm going to do work on this, remember it's always the lowest, the highest. So this case it'd be 8 choose 1, and then 0.2 to the first power, 0.8. All right, 8 minus 1 is 7, and then plus plus 8 choose 8, 0.2 to the 8th, 0.8 to the 0, 8 minus 8 being 0. That would be the work that we'd show on a test if we were doing this now. I want to show you something about this. I want to show you how this problem relates directly to the binomial. We're relating it directly to the binomial. You're like, how did this equal that? That's a really good question. All right, so I want to know how that equals a binomial. What about this? 1 minus 8 choose 0, because that's that value. 1 minus 8 choose 0. And that probability was 0.2 to the 0 times 0.8 to the 8th. This part right here simplifies to 1. This also simplifies to 1. So this becomes 1 minus 0.8 to the 8th power. So either way, you're going to get the same answer. All right, either way you do it, you'll get the same answer. And our answer for this problem was 0.8322, and that was the answer to problem number 8. Okay. The next one, number 9. 30% of candies in a bag are brown, 20% are red, 20% are yellow, 15% are green, and the rest are blue. If 2 candies are randomly drawn from the bag with replacement, what's the probability they are the same? So we're drawing them with replacement, which means the probabilities are not changing. So that was nice to know. All right, that was a good thing to know. And I'm just going to go ahead and write those down because this helped me out when I was actually setting this problem up. 0.30, 0.2, 0.2, 0.15, and the rest are blue. So I'm going to put little plus signs there, and I'm just going to add those up in the calculator. All right, and see what they add up to. 0.3 plus 0.2 plus 0.2 plus 0.15. So I added those up, and I get that that equals 0.85. Well, that's not a valid probability distribution, but here it says the rest are blue. So 1 minus 0.85 equals 0.15. So I now know 15% of them are blue. It says if 2 candies are drawn at random from the bag, what's the probability they are the same color? Oh, well, that means I could draw 2 red, 2 brown, 2 yellow. So that's going to look like this: a brown and a brown, plus a red and a red, plus a yellow and a yellow, plus a green and a green, plus a blue and a blue. Well, the probability of a brown is 0.3 times 0.3 plus the red, 0.2 times 0.2 plus the yellow, 0.2 times 0.2 plus the green, 0.15 times 0.15. And we already said the blue was also 0.15 plus 0.15 times 0.15. So let's do that in the calculator real quickly. So essentially, we're taking the calculator and we're going to go 0.3 squared plus 0.2 squared. So 0.3 squared plus 0.2 squared plus 0.2 squared plus 0.15 squared plus 0.15 squared equals 0.215. So the answer for this problem, for problem number 9, is 0.215. Moving on to problem number 10. A machine has 5 components. If any one fails, the machine fails. So this is essentially an at least, because they're saying if at least one fails, the machine fails. Whenever they say that, I immediately think this might be a complement problem, but I need to read further. 3 of the components have a 0.99 chance of failing. One of the components has a 0.97 chance. The last component has a 0.98 chance of failing. It is reasonable to assume that the components' failures are independent. That's important. That means I can multiply them. What is the likelihood the machine does not fail? Oh, well, wait a second. This is not going to be a complement problem because they don't want the machine to fail. They want the machine to work. And we have 5 components. And so we have 1, 2, 3, 4, 5 components. And we don't want the machine to fail. We want every single one of the components to work. So the probability the first component works is 0.99. Well, we have three components that have the 0.99. The next component has a 0.97. And the last component is 0.98. So I just need to multiply those values together real quickly. And I'm not, paper's not slipping. But if I go, you take the calculator, and I go 0.99 times 0.99 times 0.99 times 0.97 times 0.98. I end up getting 0.9223. All right. So the answer to number 10 is 0.9223. All right, now some of you are going, hey, he truncated and I rounded up. That's fine, we got it. So if you have 0.9224, you're good to go. All right, number 11. The distribution of colored candies in a bag are as follows. All right, assume that the candies are drawn with replacement. What's the probability the first candy drawn is the first brown is the third candy drawn? Okay, so here we go, and I can do this right on this page. They're drawn with replacement, so probabilities aren't changing, and we are looking at drawing three candies. The first brown is the third candy drawn, so this is brown, and these are not brown. The probability of brown is 0.3. The probability of not brown is 1 minus 0.3, which is 0.7. Once again, this came from 1 minus the 0.3. So I just need to multiply those values out real quickly. And we have 0.7 times 0.7 times 0.3. So that's 0.147. All right. So the answer to number 11 is 0.147. All right. For flights from a particular airport in January, there's a 40% chance a flight is being delayed because of icy weather. If a flight is delayed because of icy weather, there's a 20% chance that the flight will also be delayed because of mechanical problems. If a flight is not delayed because of icy weather, there's a 10% chance that it'll be delayed because of mechanical problems. The table organizes the above information. Now, real quickly, this table was built based on that information, so you didn't have to do the work. And so the question for number 12 is, if one flight is selected at random from the airport in January, what's the probability we'll have at least one of the two types of delays? What are my delays? We have an ice delay or a mechanical delay. So if we have an ice delay or a mechanical delay, then we have at least one. So at least one, and when I say at least one, that means we could have had both. So the fact that I could have an ice delay or a mechanical delay, and I hear that word or, makes me think, oh, probability of A union B equals the probability of A plus the probability of B minus the probability of A and B, where one of them is the ice delay and one is the mechanical delay. Well, the probability of an ice delay is 0.4. The probability of the mechanical delay is 0.14. All right, but we need to subtract out the intersection, so pay very careful attention to this. Here's my ice delay, and here's my mechanical delay. So my intersection is 0.08. So for this problem, I would use the general addition rule, and we go 0.4 plus 0.14 minus 0.08. So that ends up giving us that number 12. Number 12 is just 0.46. All right, number 12 is 0.46. Okay, moving to 13. Well, we have the same scenario, so I'm not going to reread the scenario. all right, but it's exactly the same scenario as the one above. It says, given that a flight is delayed, and they gave us the table, given that a flight is delayed because of ice, what's the probability that it did not have a mechanical delay? So anytime I see the word given, I write it down. I just go, okay, given. And I also know that there needs to be an intersection of some sort on top. Well, what was I given? Given that the flight is delayed because of ice. Okay, that's 0.40. What is the likelihood it did not have a mechanical delay? Oh, so this is 0.32 because that's my intersection right there. So 0.32 divided by 0.4 equals 0.8. So number 13 equals 0.8. Number 14, Mr. Spencer travels through 2 intersections with traffic lights as he drives to HEB. This is a really key phrase, 2. The traffic lights operate independently. Oh, that's another important thing. The probability that both lights will be red when he reaches them is 0.035. The probability that the first light will be red and the second light will not be red is 0.015. What's the probability the second light will be red when he reaches it? Okay, so when I read this problem, here's what I read. I read that I have 2 of something. I have 2 of something, and and to be honest, this is a tricky problem initially. It really is. I immediately go, gosh, I'm not sure what to do, but let's go ahead. Since I have 2 of something, we know that a table solves a lot of problems that require 2 of something or a sample space. So let's see if that helps. All right, so let's see if this helps. So we have the red light, and I'm going to say red, and this is and then not red. And I'm going to call this the first light. I'll put a 1 in front of that for the first light. First light is red, first light is not red. We know this number is 1.0, that's good. Then when we go to the next one, we have second light is red, second light is not red. All right. The probability that both lights will be red when he reaches them is 0.35. Oh, so red and red, this is 0.35. We know this. The probability that the first light will be red, that's this one, and the second light will not be red is 0.15. So this is red, this is not red, this is 0.15. I was like, oh, so the probability that the first light is red is the sum of those 2, which gives me 0.50. Okay, great. I got that far. What's the probability that the second light will be red when he reaches it? Ooh. Second light's red. I don't have that information. I'm missing that. So that's a little bit of a problem, and this is what was tricky about this. But this is independent. So the probability of A and B equals the probability of A times the probability of B. This is the intersection, and I know this is the intersection, is right here, where they got circled. Okay, so my intersection is 0.35. I know that. I know the first light has a probability of 0.5. So now I'm only looking for B. And when I divide both sides by 0.5, I end up getting 0.7. So number 14, the answer is 0.70. All right, moving on to number 15. By the way, these are not real numbers. They have a much higher survival rate. So Kodiak bears have 2 baby bears called cubs. When there are 2 cubs, the mother bear always feeds the older bear until it has its fill, and then she feeds the younger cub. This results in an unequal chance of survival for the 2 cubs. Suppose that the older cub has a 95% chance of survival. If the older cub survives, the younger cub has a 60% chance of survival. If the older cub does not survive, the younger cub has an 80%. So they set up this table. And okay, so here we have Older lives, younger lives. Well, that's 2 cubs living. Older cub lives, younger dies. That's 1 cub. Older dies, younger lives. This is 1. And the chance that both die. So what's the probability that 1 cub survives? Well, I kind of jumped ahead and filled out the 2 1s and the 1 zeros. So as it turns out, this right here represents the probability that 1 cub lives. And this represents the probability of 1 cub living. So I can add those 2 together. 0.38 plus 0.04 equals 0.42. So the probability that a single cub lives is, that 1 cub lives is 0.42, because the older lives, the younger dies, or the older dies and the younger lives. There's no intersection with this. You can't have, because if you have the older live and the younger live, then you have 2. The only one that, so this right here that has, these are mutually exclusive. So I can add them together and there's no intersection. And that would be the answer to number 15. Please make sure that your work is shown neatly, nicely, in an ordered manner so that we can follow it for this test in order for you to receive your credit.